Hi, today we're going to talk about limits when a limit doesn't exist, which seems kind of odd. And I kind of put up an informal idea of what a limit is. This is kind of, what we think, not the epsilon delta, kind of just informally what's happening. A limit L is the real number. A function approaches as x approaches the value a. We're taking the limit as x approaches a, or as x approaches infinity or in positive infinity. We've seen those kind of things. And I kind of underlined and boxed the parts that are we want to focus in on. It is the real number. The being singular, we proved that a limit is unique if it exists. And a limit was a real number. Now, sometimes a limit doesn't satisfy this criteria, but we still can use the concept of a limit and kind of cheat a little bit. Extend the idea is a better way of saying it. Mathematics is all about extending what we have to more situations to make it useful in situations that don't apply directly. And so we're going to extend the basic idea to circumstances when a limit doesn't exist, but we can still kind of get some idea of a limit. So how might that occur? Well, let's consider an example, and I'll introduce with an example. The limit as x approaches 2 of a function f of x where f of x is a piecewise defined function. It is 3x plus 5 if x is less than 2, and x squared plus 6 if x is greater than 2. Greater than or equal to 2. Doesn't really matter either way. Now, remember when we talked about limits, we had to approach a particular value, and it didn't matter which side of a we approached from. I should have gotten the same result. And notice in this particular case, if I approach x as x approaches 2 from values that are less than 2, then if x is less than 2, then f of x approaches the value 11. However, if x is greater than 2, f of x approaches the value 10 as x approaches 2. So it depends on which side of 2 we're approaching from. From one side, my functional value is approaching one thing. From the other side, my functional value is approaching something else. We could have, in this case, and this is a very rough sketch of this function, and so the first part is a line with slope 3 and y-intercept 5, and so it looks something like this. And this is the value 2. And so on this side, my functional value is approaching the number 11. However, on the other side, this is a quadratic, a parabola, has a graph of a parabola, and it would be the vertex would be at 0, 6, but we don't really care about that. We get something that looks like this. And so this is a very rough sketch of the graph. And notice from one side, as I approach from the left, my functional value is approaching 11. From the right, my functional value is approaching 10. So therefore, because it doesn't approach a singular value, the limit does not exist. However, we can kind of explain how and why it doesn't exist. And what we can do is kind of look at each piece separately, each side separately. And we get what are called one-sided limits. One-sided limit, we only consider one side at a time. And so the limit as x approaches 2 with a kind of negative exponent. That means from the left, x is strictly less than 2 in this case. Well, that value does exist. That value is 11. The limit as x approaches 2 from the right, with a kind of plus as an exponent, that value is 10. These one-sided limits exist. 10. And there is a theorem in the book that says the limit as x approaches a of f of x equals L if and only if. In other words, it works both directions. The limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x is equal to L. So in order for the limit to exist, both one-sided limits have to exist and be the same real number. If both one-sided limits exist in the same real number, then the limit exists and is that same real number. So in this case, the limit does not exist, but the one-sided limits do exist. And it kind of describes what's happening to this, function. This function is said to have a jump discontinuity. We will get to this more later when we talk about continuity, but I will mention it right now, a jump discontinuity. So let's look at another situation here. I don't have my eraser close. And let's see, does the limit exist? Suppose I have the limit as x approaches 3 of f of x, where f of x, again, is a piecewise defined function. This time, x squared minus 7x plus 12 over x minus 3 if x is less than 3, and 2x minus 9. 2x minus 9, that's not what I want. 2x minus 7 if x is greater than 3. There we go. I think that's better. Okay. Now notice this function is not defined at x equals 3. That has nothing to do with whether the limit will exist or not. We don't care what happens at the functional value. The fact f of x is not defined at x equals 3 has nothing to do with whether the limit exists or not, with the limit existing or not. It is totally irrelevant. What is relevant is, because I have a piecewise defined function, I have to consider the limit from both sides. And we're going to, compare that theorem over there. So the limit as x approaches 3 from the left, in that case, the function that I'm looking at is the function when x is less than 3. And so this would be x squared minus 7x plus 12 over x minus 3. I don't need that bracket. And notice here, this is our indeterminate friend. And so we have to do more work. This would be x minus 3, x minus 4 over x minus 3. This reduces. And the limit as x approaches 3 from the left of x minus 4 is negative 1. Okay? So now let's consider the limit as x approaches 3 from the right and see what happens. And so the limit as x approaches 3 from the right, in this case now I'm using the bottom piece, 2x minus 7, and in this case there's nothing unusual going on. We can just go ahead and take the limit, and this equals -1. And notice these are the same. And so, based on the theorem that I just erased, since the limit as x approached 3 from the left was equal to the limit as x approached 3 from the right of the function f of x, so the limit as x approaches 3 actually does exist in this case and equals -1. Even though the functional value is not defined, basically what happens in this particular situation is the two pieces kind of line up. There's a hole, but basically, and I'm not going to try and draw the graph, but basically you have this kind of situation at x equals 3. One function kind of ends the same place the other function begins. There's a hole at x equals 3 because the function isn't defined at x equals 3, and this is actually going to be called a removable discontinuity. Again, we'll talk about that later, but I might as well introduce the concept now. This has a removable discontinuity. Okay? What if I have something like, let me eliminate this here, and let's look at another situation that will require us to deal with two sides separately, and that is our old friend absolute value. What if I have the limit as x approaches 2 of x squared minus the absolute value of 3x minus 6 minus 4 all over 2x squared minus 5x plus 2. Okay, again, this is indeterminate, so we're going to have to do some work here, but the absolute value is a piecewise defined function. Remember, absolute value is a piecewise defined function. So that means this thing is going to have to be considered using one-sided limits. And so the limit as x approaches 2 from the left, we have to get rid of this absolute value. This x squared, let me just rewrite the original, minus the absolute value of 3x minus 6 minus 4 all over 2x squared minus 5x plus 2. As x approaches 2 from the left, remember x then is less than 2. And so the inside of the absolute value is negative. Go back to the algebra video that I did. That means the absolute value of 3x minus 6 is really the negative of 3x minus 6. And so this becomes the limit as x approaches 2 from the left of x squared plus 3x minus 6 minus 4 all over 2x squared minus 5x plus 2. It's really a double negative. This is really minus the negative of 3x minus 6 when I take it out of the absolute value. And so I'm going to kind of do this in two columns. that means continuing on up here, I get then the limit as x approaches 2 from the left of x squared plus 3x minus 10 over 2x squared minus 5x plus 2. It's still indeterminate. Still a 0 over 0 form, and so we can go ahead and factor. This is x minus 2 times x plus 5. This is x minus 2 times 2x minus 1. Again, I'm kind of using the fact firsts have to be product of first, lasts have to be product of last. Works great when you're doing quadratics, which is the limit as x approaches 2 from the left of x plus 5 over 2x minus 1, which is, we can now evaluate the limit, 7/3. On the other side, we would have the limit as x approaches 2 from the right of my original function. I'm just going to recopy that. And now, since x is greater than 2, the absolute value, what's inside the absolute value, is itself. And so this becomes the limit as x approaches 2 from the right of x squared minus 3x minus 6 minus 4 over 2x squared minus 5x plus 2. Okay, the absolute value is just what's on the inside. So the negative stays, and this absolute value, we get rid of the absolute value because it's positive. And so therefore, this just becomes a negative of 3x minus 6. Which then gives me, going over here, the limit as x approaches 2 from the right of x squared minus 3x. I got a plus 6 minus 4 is plus 2 over 2x squared minus 5x plus 2. And you can probably guess at this point that we are going to come up with different values here. Limit x approaches 2 from the right of x minus 2, x minus 1 over x minus 2, 2x minus 1 gives me limit x approaches 2 from the right of x minus 1 over 2x minus 1, which is 1/3. And so, since the limit from the left is not the same as the limit from the right, the limit as x approaches 2 of this function does not exist. Okay? This is one situation where a limit doesn't exist, but we can still find limits. That is, we don't get a unique real number, but we have basically two different real numbers that the function is approaching, one from one side, one from the other. Another situation where the limit doesn't exist is when the function doesn't approach a real number. For example, let's consider the limit as x approaches 2. Seems to be the, let's pick a side here. Let's go 2 from the left, actually. Of x plus 4 over 3x squared minus 5x minus 2. And notice in this case, my numerator is approaching 6, my denominator is approaching 0. This is not indeterminate. This limit doesn't exist. It's actually going to be some kind of infinite. Limit will not approach a real number because the function blows up. It either approaches positive infinity or negative infinity. And so because it still is in some respect approaching something, even though it's not a real number, we're going to extend our concept of limits and use that to say that we are approaching an infinity. Now, how to determine which infinity? The function is approaching. And this is different than what is done in the book. But this is how I would expect you to do it. Did you catch that? This is not what is done in the book, but this is what I expect you to do. So, I know that this is going to be infinite because, again, my denominator is approaching 0, my numerator is not. So the question then becomes, what can we do about it? Limit x approaches 2 from the left. I'm going to rewrite the problem here. Okay. Since my denominator is approaching 0 and this is a polynomial, we can still factor that. X minus 2, 3x plus 1. And now let's see what each particular factor approaches. As x approaches 2, this numerator is approaching 6. The first factor is approaching 0, but the important part is which side of 0 are we on? Since x is less than 2, x minus 2 is approaching 0, but it's actually negative. It never is really 0. Again, you have to get into your brain that limits, you do not let the value equal what we're, the limit value, what we're approaching. We are approaching 2. It never actually equals 2. That's a hard concept to kind of get used to. X is never 2. It is always less than 2, which means this is always negative. This factor is going to approach 7. And so I have a positive divided by negative times positive, and so therefore the overall limit in this case is going to be negative infinity. And what we mean by that is we're not saying that this is in negative infinity is a real number. This is what the function approaches. We are using the concept of a limit as an approaching something, in this case, approaching an infinity. Let's compare this to another very similar problem. X approaches 2 to the left. From the left, x plus 4. And I'm going to change my denominator this time to be 3x squared minus 14x plus 16. It's still, numerator is approaching 6, denominator is approaching 0. That part is the same, which means we will factor. Of course, factorization is going to be a little different. X minus 2, this time the other factor is going to be 3x minus 8. And if you check it, it will give us what we want. My numerator is still approaching 6. The first factor is still approaching 0 from the negative side. The second factor this time, however, is approaching negative 2, which means the overall fraction here is positive. And so in this case, the limit is positive infinity. So even though this limit technically does not exist, because it approaches something, an infinity, we write it as, we kind of borrow the terminology and the notation and say the limit is, well, in this case, negative infinity, in that case, positive infinity. By the way, these functions have what is called an infinite discontinuity. At x equal 2, both of them do. And again, we will talk more about that when we get to talking about continuity coming up soon.